where she contributes to advancing the frontiers of quantum computing through both research and software development. She holds both BS and MS degree from ISER Pune. With approximately 4.5 years of combined experience in academia and industry, she brings a unique hybrid expertise that bridges theoretical research with practical engineering applications in quantum technology. At IBM, her work spans quantum algorithm development, quantum software engineering, and contributions to quantum platforms such as Qiskit, aligning with IBM's global mission to make quantum computing accessible and impactful. Her profile reflects a rare combination of research level knowledge in quantum information science and hands on skills in software engineering, allowing her to design and implement solutions that push the boundaries of quantum systems. Janani's academic training, rooted in strong technical foundation in physics, computer science, and closely related discipline mathematics, has equipped her with both the conceptual depth and programming expertise necessary for the evolving quantum era. By integrating theory with practice, she plays a pivotal role in shaping the future of quantum computing research, software ecosystem, and real-world applications. We are thankful to you for accepting our invitation for being a speaker in this program. Thanks. Over to you.
Thank you for such a warm welcome. Firstly, I'd like to apologize to the participants for the slight delay. As I said, I was running late from a previous meeting. Let's get started in a few minutes. Yeah, just a second. Let me share my screen, check if everything's in order. Okay. Is my screen visible?
Yes, your screen is visible.
Okay, let's get started then. Hello, everyone. Welcome to this session in QT-06 on post-quantum cryptography, also called as quantum-safe cryptography. I'm Janani, and today let's discuss this topic. So, firstly, I always like to define some lecture objectives which convey the essence of what is meant to be discussed in this lecture and also what should be the takeaways. So in this particular lecture, what are some of the lecture objectives? So we will discuss, first of all, what is quantum safe or post-quantum cryptography. Because there is quantum in the name, a lot of people presume that post-quantum cryptography or quantum safe cryptography has it's actually part of quantum computing. While it deals closely with what quantum computing can do, quantum safe cryptography or post-quantum cryptography is actually classical. So, and as I explain what it is, I think that it will make a lot more sense as to why it is classical. But yeah, that is one of the main important takeaways, I would say, from this particular lecture. Post-quantum cryptography or quantum-safe cryptography is actually not quantum. It's not part of quantum computing. There's not much quantum involved in the in designing these protocols itself, but it deals closely with what quantum computing can do. So aside from that, what are security risks that come from quantum algorithms, and what is the timeline, right? Because I think the realistic sort of outlook for what post-quantum cryptography needs to do, or what even quantum computing can do in terms of affecting the current encryption schemes, it's a bit there's while we can discuss things theoretically, it's also important to consider the practical aspects of how the current quantum computing status can affect the current encryption schemes and basically cyber security. So after that, what is the adoption and necessary measures that need to be taken? Do they need to be taken? Why they need to be taken? And what is being done? So some of these things will be the takeaways from this lecture. So quantum safe or post-quantum cryptography, what is it? So it is a new set of cryptographic algorithms designed to secure information against both classical and quantum computers. Now, the reason why I mentioned that post-quantum cryptography is actually classical is because, as you know, the current existing cybersecurity is built upon like some cryptography schemes, which we will also slightly discuss in the upcoming slides. But importantly, like the current, for because of the quantum computing is a new technology, right? And with the advent of quantum computing, how has cybersecurity been affected? So if you look at the history of quantum computing, we will discuss this again in detail in the upcoming slides. But one of the biggest reasons, like I would say, if you look at the timeline of how quantum computing evolved and why people started taking it seriously, as we all know, Shor's algorithm is one of the core sort of algorithms which really sort of put quantum computing, in front of everyone. And the reason why Shor's became very prominent is again actually related to the consequences of what it can potentially have on cyber security. Honestly speaking, and so this is a field. So both quantum computing, quantum computing, of course, developed independently, but post-quantum cryptography became a sort of significant thing to study, or like, let's say, this actual cryptography or cyber security standards have had to evolve because of the advent of quantum computing. So post quantum cryptography is basically coming up with new sets of cryptographic algorithms designed to secure information both against classical and quantum computers. It's a proactive measure to protect sensitive data from future attacks by powerful quantum computers. As we know, quantum computers are still like developing, but they're evolving rapidly, right? So again, this is something we will discuss in the upcoming slides, but this the development of this field is a proactive measure. And why it's a proactive measure and not just like a measure being taken, or which is like sort of distantly in the future, that also there is a sort of catch there, which we will discuss in the upcoming slides. I don't want to give up all the suspense right here in the second or third slide. So, okay, now why is it needed? Current public key cryptography schemes like RSA and ECC, they rely on mathematical problems that are hard for classical computers to solve, but easy for future large-scale quantum computers to solve. So the core algorithms here, we have Shor's algorithm, which is a quantum algorithm which can effectively break these widely used schemes. And then we also have Grover algorithm, which can potentially speed up brute force attacks on symmetric key algorithms. Although it's not to like a great extent, it can sort of speed up the attacks to some extent. So first of all, what is encryption, right? Encryption is the process of converting readable information, which is in plain text, for example, into an unreadable form, or basically to sort of your whatever information we might have, like which is being cast out on the internet, which can be accessible to many people from many places. We want these things to be secured under certain layers, right? So when these things are being sort of, so that's why we have encryption. And this encryption, like the basics of what makes an encryption is that you convert readable information, which is in plain text, into an unreadable form, which is in ciphertext, right? And what is decryption? Decryption is the reverse process where you convert this ciphertext back to plain text. And this is achieved using an algorithm and a key. So there are two main types of encryptions. You have symmetric key cryptography, where you use the same key for both the encryption and decryption. So you can think of it like a shared secret, right? And asymmetric key cryptography, or public key cryptography, you use a pair of keys, a public key for encryption and a private key for decryption. So the public key can be shared widely, but the private key remains secret, like in RSA or ECC. Now, the main important thing to keep in mind is that the safety of several encryption schemes today is dependent upon the difficulty of solving certain mathematical problems with classical computers. So, for example, if you take a look at, let's go to the previous slide. If you take a look at RSA, this is a cryptography scheme which was designed based on the difficulty of factorizing a large number, right? So you can, so if I say name the prime number, so what do we do when we factorize a number? We we basically will we will sort of, okay, we factorize it in terms of primes, right? So if you take say I have to find the first n prime numbers, okay, and n is equal to 100. This is fairly easy for us to come up with. But how do you, if you have like a 6 or 7 digit number, how do you find out whether it's actually a prime number or not? It could very well be a prime number, right? It's so, say if it's even, then you can immediately tell it's not a prime number. That's fairly easy. But if it doesn't end in an even number, and it's not evident, like right when you see to guess whether a number is a prime number or not. And it's all the more difficult if you have to, if you have a multiple of such a large prime number. How do you easily find out whether it can be factorized or not? So yeah, so the essence of, like, say, several encryption schemes today is dependent upon the solving of dependent upon the difficulty of solving certain math problems with classical computers. So what is the source of security here? The security of most modern public key cryptography relies on the difficulty of certain mathematical problems for classical computers, which we just discussed. For example, RSA security is based on the difficulty of factoring large prime numbers. Similarly, ECC, or elliptic curve cryptography security, is based on the elliptic curve discrete logarithm problem. Okay, so ECC is something basically which takes into account the algebraic, like the algebra behind the structure of an ellipse. Let us say, okay, it's so these are in a sense these are one-way functions where or like one-way functions, loosely calling them that. It's like they are easy to compute in one direction. For example, if you have to multiply two large prime numbers, it's pretty easy, right? But if you have to do the reverse, it's extremely difficult. So find the original primes from their product. So if I have a large number, which is a multiple, which is a product of two large prime numbers, how would you guess? So normally, if we had to find a prime number of a given number, what do we do? Like, say I'm just like talking about the most basic brute force classical method. So if I have a number, say 37, right, and I want to know if it's prime or not, then what would I do? I would try to first think about the square root of 30, like the nearest square number to 36. Or I can just take the square root and take the, I can take the largest, I can forget the remainder and just take the multiple. And then I need to check if it is divisible by every prime number lower than that number, right? So then I can, so for like say 37, it would be 25 is the nearest square number, right? So 5 times 5. So is 37 like divisible by any prime number under this number, right? So like for smaller numbers, this is relatively easier to do, but for larger numbers, it's difficult to even think about what are the prime numbers, right? You can name up to maybe even 1,000. But after that, it's going to get progressively more difficult to even know if a number is a prime number or not, let alone if it is a composite of two, if it's a product of two large prime numbers, right? However, as we know, Shor's algorithm is capable of kind of factorizing. So, okay, so like now let us introduce Shor's algorithm and briefly discuss it, or like we'll get to that. But for now, what is Shor's algorithm? It's a quantum algorithm essentially for integer factorization. It was developed by Peter Shor in 1994. It factors large integers in polynomials time, and it's an exponential speed up over the best known classical algorithms. And this makes it pose a significant threat to widely known like public key crypto systems, mainly like RSA and other, algorithms which rely on, the difficulty of factorizing two large numbers to be the key behind that encryption scheme being secure. So what are the quantum threats to cryptography? So for example, you have Shor's algorithm, which is a quantum algorithm that can do integer factorization exponentially faster than a classical algorithm. So this directly threatens the security of widely used public key schemes like RSA and ECC. So it would allow an attacker with large-scale quantum computer to easily compute a private key from its public key, and this effectively makes that encryption scheme useless, right? So similarly, Grover's algorithm can also have some sort of, it can also, affect, like it can potentially be a threat, but dealing with this is kind of not too difficult, because if you just increase the key size to a bit, like if you increase the key size by a bit, you kind of can at least deal with with you can deal with it effectively. So mainly let's talk about Shor's algorithm and how it can affect the existing sort of encryption schemes. But like, let us do a realistic assessment, not just so when we say Shor's algorithm can solve integer factorization and this poses a huge threat, we are talking about factorizing large numbers. And so if so this now the question becomes, can Shor's algorithm effectively factorize a large number? So that will be the realistic assessment. So so if you want to realistically sort of understand what threat quantum computing is posing today, like right now, for these encryption schemes, to do that you have to know how well Shor's algorithm on current quantum computers, how well can it potentially solve, say, factorizing a large integer. So for that, we need to understand the fundamentals of Shor's algorithm. So basically, it solves a prime factorization problem, and it can help factor large composite numbers. Say if you have n equal to pq, then then it basically can help you find out what are p and q. So general number field sieve is supposed to be one of the best classical approaches for solving this, and the complexity of that is given by this. But on a quantum computer with Shor's algorithm, it takes much lower. So you see, you have gone from exponential time to polynomial time, right? So this is a huge. It's basically an exponential speed up. So this makes. So how does it actually solve the problem? So it makes use of it basically reduces the factorization problem into an order finding problem. And with the help of quantum Fourier transform, which is sort of subroutine of this Shor's algorithm, it helps to provide an exponential speed up over the best known classical algorithms. So how do you, let's actually take the integer factorization problem and understand how we can transform it into something that can be a period finding problem, right? So consider integer factorization. Okay, say I am picking the problem of finding the prime factors of the composite number n, where I'm saying n is equal to, so for example, if you have 15, you have factors of 15 being 3 and 5, right? So for sure, what is the transformation we are going to do? We convert this integer factorization into a period finding problem. Sorry, I'm not keeping track of time. Okay, we have a lot of time. Okay, so we want to transform this into a period finding problem. So what is the period finding problem? So if you have a function f of x is equal to a to the power x mod n, find its period r. So the period r is the smallest positive integer such that a to the power x plus r mod n is equal to a to the power x mod n for all x. So essentially, if you plot a function, you'll see that the function is repeating after a specific sort of positive integer n. So that becomes the period. So if r is found, the factors of n can be derived from the GCD of a to the power r by 2 minus 1 comma n and the GCD of a to the power r by 2 plus 1 comma n. So this basically gives you the two factors. So if I have n is equal to pq, p will come from this GCD and q will come from the other GCD. So key concepts to understand key concepts which are required to understand Shores are: what are periodic functions, what is the modulo arithmetic, and what are unitary operators. Now, unitary operators, I hope everyone is familiar with by now, because this is QT-06, and we have had a lot of quantum fundamental courses where any gate, if you want to create a quantum circuit, any gate is basically any gate that is reversible in a sense would be a unitary operation. For example, if you have a reset or a measure, that is not a unitary operation, that will be a non-unitary operation. However, if you apply, say if you apply a Hadamard gate, an X gate, an RX gate, these are all unitary operators, because you can reverse these by you can reverse these operations by implementing their inverse, for example. So what are periodic functions? So functions that repeat their values at regular intervals will be periodic functions. A very simple example is the cosine function, the sine function. So after, like, say 2 pi, you will see that sine function is repeating, and the period of like cosine is also 2 pi, but the place where it starts repeating can change, right? So these are all examples of periodic functions. And what is a modular arithmetic? Operations involving reminders after division. So say, for example, if I have 7 mod 5, basically what mod does is it returns the remainder after dividing 7 by 5. So if I divide 7 by 5, that's going to be 2 point something, right? So it returns, will basically give me like 1 point something. But if I have to express 7 in terms of 5, it's basically 7 is equal to 5 into 1 plus 2, right? That plus 2, the modular arithmetic basically returns the remainder. Now, in terms of quantum subroutines, you will have to understand what is quantum Fourier transform if you want to understand what how Shor's algorithm will work, because the pipeline is basically you understand quantum Fourier transform, then you understand quantum phase estimation, and then how that can be generalized to implement the Shor's algorithm, which solves a specific application of, say, factorizing a large composite number. So it is basically an analog of the discrete Fourier transform. It is used in quantum phase estimation to extract the period information from the quantum state. And the inverse quantum Fourier transform is also important, because once you get the phase information, you want to be able to transform it back into a measurable period. The period here is referring to the periodicity of that function, right? So if you want to, so the inverse QFT is also very significant. In fact, that's the part of the algorithm. That is what you will actually see coming as a part of quantum phase estimation. So here, if I want to implement a simple quantum Fourier transform circuit on, like, say, n qubits, this is what it's going to look like. You'll have a Hadamard, then you have a controlled rotation, controlled R2, then you have a controlled R3, so on up to controlled Rn. Then you start on the second qubit, where you have a Hadamard, you have you have a controlled R2, so on up to controlled Rn minus 1, and until you come to the last qubit, where you only implement a Hadamard, and then you're going to do n swaps. So now say if I want to do quantum phase estimation, how is that done? So it's a coarse quantum subroutine used in Shor's algorithm. So what does it do? It estimates the phase phi of an eigenvalue e to the power 2 pi I phi of a unitary operator up to a given precision digit. Now, we understood how to implement quantum Fourier transform, that this is the circuit for sorry, I need to go back. So this is the circuit for implement a QFT. So if I want to implement a QFT inverse, basically if you consider the whole thing as a set of unitary operations, and a single operator, you just take the dagger of that operator. Dagger in the case of quantum computing, because these are unitaries, we have the condition that the complex conjugate transpose of the matrix is equal to its inverse. So basically any U dagger is I. So basically this is the QFT dagger circuit. So it's the reversed circuit which we have as part of the quantum phase estimation. But before that we have several Hadamards and we have controlled unitaries going from here up to like the second last digit. So here we have, so okay. So this is the quantum phase estimation subroutine. Now, how does the period finding help factorization? Now, this is an important question to understand, right? So the core idea relies on a property of modular arithmetic that relates to the difference of squares. So we know that a to the power r can be written as 1 mod n. So since r is even, we can write this as a to the power r minus 1 is equal to 0. Mod n, and this can be factorized, right? You can write this a to the power this as a to the power r by 2 whole square. So the very basic the very basic identity which we use, a square minus b square is equal to a plus b into a minus b. So that is what we're doing here. And we have a to the power r by 2 minus 1 times a to the power r by 2 plus 1 should be 0 mod n. Now this means that n must divide the product a to the power r by 2 minus 1 and a to the power r by 2 plus 1. So this is how we are concluding that the GCD of this comma n and this comma n will give us the two like factors of n, which basically that's how we will be able to do the prime factorization. So just to come up with to actually illustrate the exact steps of how Shores can be implemented. So we always have a classical, so this is a very high level overview of the steps. So you have a classical pre-processing where you choose a random integer random integer a such that 1 less than a less than n. So this is for factorizing a number n, right? How do you do that? Then you calculate the GCD of a and n. If the GCD of a and n is not 1, then a is a factor. So we have already found one of the factors without doing anything. But if that's not the case, then you will have to implement quantum period finding, right? So construct a quantum circuit to implement the function f of x is equal to a to the power x mod n. Then you use now, so this is one of the sort of steps which is like related to how you need to implement Shores. Then you use the quantum phase estimation with the unitary operator uy is equal to ay mod n to find the period r. Then you have a classical post-processing which needs to be done. So from the measured value s by r, you use techniques like continued fractions to find r. Then you calculate the GCD of a to the power r by 2 minus 1 and n, and GCD of a to the power r by 2 plus 1 and n. These will likely yield the factors of n. Now, if r is odd, okay. So firstly, it's not guaranteed that this would immediately help you find the factors on the very first try. It may be the case that it does not, because you did not choose a good a in the beginning. In that case, you will have to repeat this process. But even otherwise, if r is odd or a to the power r by 2 plus or minus 1 is a multiple of n, you will have to repeat the process with a different a. So these are the conditions where you may have to implement this algorithm once again. Now, this may seem like a lot of steps, but it is still more efficient than the brute force method that we would do otherwise, where we have to, factorize a large number into its two prime factors. So under these subroutines, I mentioned you use quantum phase estimation with the unitary operator uy equal to a to the power y mod n to find the period find the period r. Now, what does this actually involve? You need to prepare an initial superposition, then you need to apply controlled unitary operations, then you perform the inverse quantum Fourier transform, then you measure the output qubits to obtain s by r, where s is an integer. Basically describing, so here you have QFT inverse, This is the quantum phase estimation circuit itself. But when you're sort of applying it for Shor's, it's a subroutine. It's not everything. So you have to design the input states and the output states in such a way that you're actually, trying to implement Shor's algorithm. So how can this be implemented in Qiskit? You need to initialize qubits and registers, implement the modular exponentiation operation, so the U operator, as a series of quantum gates. So this is often the most complex part. But now I want to come back to the original topic of this, talk, which was post-quantum cryptography, right? Now, just at this step, you guys would have realized the complexity of what all is needed to implement Shor's algorithm. Now, this is theoretical complexity, what we've discussed so far, but there are several practical complications as well. Now, even though our quantum computers are improving day by day, as at the current moment, the depth of you can see, right, how many gates and how many, what all is required for just the number 15. This is not even like a huge number. This is for the number 15, and just for the number 15, the kind of circuit you will have will be very deep, and there will be a lot of gates which need to be implemented for us to be able to actually implement Shor's algorithm for solving this problem. And one more, okay, yeah, let's just finish the Qiskit implementation and then I'll come back to the practical difficulties. But so you basically, as I said, this is often the most complex part. Then you need to create controlled unitary operations where the U operation is applied conditionally based on control qubits. Then you implement inverse QFT, leveraging, you can use Qiskit's built-in functions or create it manually, that doesn't matter. Then you have to measure the output register to obtain phase information, and then you have to post-process the results and analyze it in order to extract the period R. So this is an sort of an exact illustration of the checks of the steps you need to take to factorize a number 15 with using a equal to 7, right? But now I'm just going to skip this because we already had this discussion. But yeah, excuse me. Coming back to the practical difficulties, right? Now the assessment. So Shor's algorithm is a powerful demonstration of quantum computing's potential to solve in the classically difficult intractable problem of factorizing a large composite number into its two prime factors. The period finding subroutine, which leverages QPE and QFT, these are the heart of its quantum advantage for exponential speed up. But while its theoretical significance is profound, challenges remain in hardware implementation as it requires fault-tolerant hardware. You need to be now whatever I've discussed so far, this is actually in the absence of noise, right? So now imagine implementing so many gates and there is also noise. Everything will go haywire, right? So in the near term, our best shot actually, right now, the best capabilities of Shor is to be able to factorize the numbers in the range 15 to 22. So that is actually the capability of Shor's as it is as of current day, right? There are more efficient and alternate implementations of Shor's which use lesser number of qubits than what we are currently using. All that is there, but so this is the practical difficulty. However, this doesn't mean that the threat of Shor's is not going to affect the cryptography schemes and basically our cybersecurity frameworks right now. And the reason for that is now the looming threat of harvest now, decrypt later. So what is the imminent danger? Why do we need to act and kind of look at post-quantum cryptography today? So even though large-scale quantum computers don't exist yet, a threat is present today. And the threat is that the adversaries can harvest encrypted data today and they can store it. But once there are sufficiently powerful quantum computers, they can decrypt all the stored data and access sensitive information. And this is particularly dangerous for data with a long shelf life, such as government secrets, medical records, or intellectual property. So it's important. Because of this reason, it is important to come up with cryptographic schemes which will not fall even after quantum computers become much more advanced, right? So that in the future also the data which was hoped to be kept safe remains safe. So in terms of adoption, what is happening? So cryptography touches every corner of the digital world, from the internet protocols and enterprise applications to critical infrastructure and financial systems, right? So to manage cryptography effectively in the quantum era, organizations are mostly transitioning to post-quantum encryption algorithms and modernizing their cybersecurity practices. So the global efforts and sort of migration strategy that is kind of happening. So the National Institute of Standards and Technology, NIST, has initiated a global competition to standardize new quantum safe cryptographic algorithms. And this process has been going on since 2016. The goal is to sort of provide a set of standardized algorithms which can replace the current vulnerable ones like RSA, ECC, which can potentially fall to the threat of fault tolerant computers in the future, right? So whatever data is being kept is being encrypted right now, we need to kind of transition them to to sort of encryption schemes which will remain robust even under the threat of like fault tolerant quantum algorithms. Of course, so this is one of the reasons why I would say quantum kind of becomes a more regulated framework as to who can use it, because it should not be misused in the wrong hands. So the goal is to provide a set of, as I mentioned, to provide a set of standardized algorithms that can replace the current vulnerable ones. This migration to post-quantum cryptography will be a long-term complex process, right? It's not going to be a simple one. It requires updating hardware and software infrastructure across the globe. So organizations need to start planning their cryptographic migration now to be prepared. Because there is also, as I mentioned, the imminent threat of harvest now and decrypt later. So what are some current quantum safe schemes? So as of 2024, you have some standards which have been announced. So I'm not going too much into detail into this. You can like refer literature if you want to, if you're interested in kind of exploring this. But basically, now we are looking for more for different kind of hard problems, which would be much more difficult for quantum computers to efficiently solve. So you have things like lattice-based cryptography, hash-based cryptography, and code-based cryptography, as opposed to things like ECC or RSA. And you have like some protocol, like some algorithms which have cryptographic algorithms which have come out of this. Now with that, I would like to finish this session. Do you have any questions?
There are no questions posted on the chat window. So basically, I
Okay.
think there are no questions from the participants. Otherwise, generally they post it on the chat window. So we can start the next session. Around, I mean, at 3 p.m.
Yes, sure. Let's take a 10-minute break and we can resume for like,
Right.
yeah, sure.
Okay.
Thank
Thank
you.
you.